Hello, and welcome back to a video series on MAC 1140 Precalculus Algebra. My name is Sean Perry. These are guided notes number 23 in the series on section 5.1, the conic sections, parabolas. One of the main themes of this section is to look at some familiar shapes through the idea of a locus. A locus is a description of a set of points given in terms of their relationship to some other set of points. For example, a parabola can be described as the set of points which are equidistant from a single fixed point, called the focus, and a line, known as the directrix. So far, with polynomial functions, we've seen parabolas which point up or down. Why should this description, the set of all points that are equidistant from this focus and this directrix, why should that trace out a parabola? To start with, let's put our vertex at the origin, and let's put our focus along the positive y-axis at a point A. To be equidistant from this vertex, the directrix must then be a line passing through 0, negative A. And again, for simplicity, we're going to orient that horizontally so that this is our directrix here. Let's consider what it would mean to talk about the distance between a point, xy, and this line. Well, the shortest distance between the two of them is going straight towards it at a right angle here. And that would have a certain distance equal to the value of y plus a. We can use the distance formula to calculate the distance between xy and 0a. If we do that, we get the following two terms. Squaring both sides, expanding, and simplifying, we wind up with the equation x squared is equal to 4ay. And this is going to be an important base equation for us to learn. The equation of an upward-facing parabola with vertex at the origin. Notice that our a here is the same a which told us the distance from the vertex to the focus and from the vertex to the directrix line. There's a few things we can do to make this a more general picture. The first thing is I could move the vertex to an arbitrary point hk. Another thing I could do is I could orient it differently. If I interchange the roles of x and y and now have a y squared and an x which is not, then I'm going to have a parabola which points either left or right. This one, for example, with a positive 4a term, is a rightward pointing parabola. We should try to break down the pattern first for what it looks like for the orientations of my parabolas based on their respective equations when the vertex is at the origin. Here I've written all four such equations. If it opens up or down, we notice that x is squared and y is not. Opening up has a positive term in the front, and opening down has a negative term. I'm going to consider a to be a distance and so positive, and so we're actually going to consider different forms of an equation either with or without a negative sign for opening up or down. Opening right or left looks very similar, except now x and y have changed roles. Opening right is still a positive leading term as such, and opening left, we would have a negative 4a in front of what should be an x here. Now, this is for the vertex at the origin. If, on the other hand, we wanted a vertex at hk, what I would do is compose the correct transformations to shift the vertex as such. That's going to look like subtracting h and subtracting k from my y terms. Notice that everything else stays the same. Being x squared y naught is still opening up or down, with positive going up and negative going down. Likewise, y squared with x naught is opening right or left, with right going along with a positive leading term here and left going along with a negative one. The only difference between the vertex at the origin and the vertex at hk is that we now have x minus h as the thing squared here, or y minus k as the thing squared here. We have composed with minusing by h against x and minusing by k against y. For the first question in the guided notes, we want to take a look at this equation, x squared equals 24y, and we want to first decide on its orientation. We notice that it's x squared, y is not squared, so this is a parabola opening up or down, and since this leading term is positive here, this is going to open up. 4a is being played by 24. Therefore, a is equal to 6. From here, we can now sketch a quick picture. We know that the origin is at 0, 0, because there's nothing being taken away or added to the x and the y. and we know it opens up. This allows us to go up from the vertex by 6 and put my focus. The focus will always appear inside the parabola, and the directrix will appear outside. Now, if this was 6 up to get to the focus, it's going to be 6 down to get to the directrix. And if this is opening up, the directrix will be a flat horizontal line. That gives me a directrix of y equals minus 6. We need this whole equation to specify that we're talking about a line for the directrix. The next one gives us an equation, y squared equals minus 16x. Here we have y squared, and x is not squared, so this is opening left or right. And since this leading term is negative, we know that it opens left. Negative 16 is therefore equal to negative 4a, which makes a equal to 4. This gives me enough that I could start sketching a picture, granted that I know that this also goes through the origin again. Notice there is nothing subtracting or adding to the y or the x. So I put a vertex at the origin, I have it open left, and then I think a is 4, so I go to the left inside the parabola by 4 units and I get to my focus. I go to the right outside the parabola, and if this is opening to the left, I need a vertical line here to be my directrix. So that's going to be the vertical line at x equals 4 and a focus at negative 4, 0. These questions now ask for an equation given certain values for the vertex and focus. It says that the vertex is at the origin and the focus is at minus 10, 0. This right away tells me that my parabola is going to open to the left in order to encapsulate that focus. That tells me also my value for a. Since I've gone from 0, 0 to minus 10, 0, I've gone a distance of 10, and so my a is 10. That means that 10 units in the other direction will give me my directrix. But if all I want is the equation, I notice that it's left opening, so we have y squared is equal to negative 4ax. And since we found the value of a to be 10, we just plug that in, and we get y squared is equal to negative 40x. A sketch here as you go is very helpful in determining its orientation and the meaning of certain values, such as a. Here's another one. It says it has a vertex at the origin, so we put that here, and a focus at 0, 5, so it opens up. This means it has this form, x squared is equal to 4ay is what that should say. And likewise, once we know that a is equal to 5 here, that will be a 20y for our final equation. X squared is equal to 20y. This one tells us that the vertex is at the origin and the directrix is at x equals negative 7, so a vertical line. The vertical line for our directrix over here tells us that it's opening away from the directrix, that is to say towards the right. That tells us that we are looking at an equation of the form y squared equals 4 times a times x. Now a must be 7, since it's 7 units from the vertex to the directrix. Then also it must be 7 units up towards the focus, but really all we need to extract from here is a, which is 7. That means the standard form should be y squared equals 28 times x. Here's one pointed down. It says that we have a vertex at the origin of directrix of y equals 9. So if the vertex is here and y equals 9 is our directrix, the parabola opens away from that and therefore it opens down. We have a distance of 9 up to the directrix, and so a distance of 9 down to the focus. But this just tells me that a is equal to 9. We're going to have this of the form x squared is equal to negative 4 times a times y because we are pointed down. This gives me x squared is equal to minus 36y, and we're done. Here we're actually told that we have a focus at 0, 9, so up here, and a directrix of y equals negative 9. That's down here. We can see that this is a horizontal directrix, and so this must open up to enclose this focus. Now, where's the vertex? It'll be halfway between the two of them at the midpoint of the segment connecting the focus and it's the intersection of the line of symmetry with the directrix. So that actually puts the vertex at the origin. And so we have something of the form x squared is equal to 4 times a times y. Well, a was turned out to be equal to 9, so this is x squared equals to 36y. Here's another one where they give us focus and directrix. Focus at 0, minus 6, and directrix y equals positive 6. That's a horizontal line. And so that's going to give us a parabola which opens up or down. And since we have the directrix up here at y equals 6, and the focus down here at -6, that's going to give us a parabola that opens down. Since a is equal to 6, our vertex is going to be here at the origin, and we're going to have a standard form which looks like 4 times 6 with a negative sign out in front. Notice y is not squared and x is squared. So all of that together is going to give us a down-facing parabola with the correct vertex, focus, and directrix. For the next one, they've given us that the vertex is at the origin and the directrix is at y equals 1/2. Again, this is going to put a vertex below the directrix, and so the parabola is going to keep going in that direction and open downward with a focus which is just as far below the vertex as the directrix is above the vertex. So that's going to be a 1/2 for a as well. And we're going to have x squared equals -4 times ay. Put that all together and we get x squared is equal to -2y for our standard form. Number 10 gives us one with some fractions. They tell us that the focus is at this particular value and the directrix is at this particular value. I suggest beginning by plotting those points, at least roughly. -33/4 is going to be over here, and -4 will be down yonder. We have a directrix at x equals 57/4. That's this vertical line here. And we know that our vertex is going to be halfway between the directrix and the focus. So that means this distance here from one to the other is going to be 2a. You could go along the axis of symmetry of the parabola and see how far you went from focus to directrix, and that would be a value of 2a. And the vertex would be right in between them. So we could solve for that distance, which is 57/4 minus -33/4, and then divide that by 2 to get 45/4 for our value of a. Now, the vertex is this point halfway between. It's actually the midpoint of the line segment connecting the focus and the nearest point on the directrix. So this midpoint is going to be along the same vertical line. It's going to be along the axis of symmetry. So we know the y value is going to be -4, and the x value is going to be halfway between these two values. Or you could go up by a from our lowest value. There's a variety of ways to get there, but that value is in fact just 3. So we have a vertex which is going to be at 3 minus 4. Now, our equation for standard form is going to put a minus 4a in here, and we know it's a minus because we can see this guy opening to the left. We also know it's y that's going to be squared because that points us left or right, and then the -4 chooses between the two. So then we put our value for k in, y minus that, and our value for h in, x minus that. Once we do a little bit of simplification, we get y plus 4 squared equals -45 times x minus 3 for our standard form. And that was kind of nice because even though they started out with some fractions, it turned out that the vertex then landed on a whole number, and our value of a wound up canceling with the 4 up front in the formula to give us a whole number as well. So that was pleasant. At number 11, they give us another one with directrix and focus. So here I have a directrix line, horizontal line at y equals 5.5, and the focus is at 10, 12.5. So let's just really quickly sketch that in, that our focus value is here at 10, 12.5. Now, that means it's going to be a vertical distance down to this directrix from this point here to this point here on the directrix. Now that distance is 2a. We want to find out what a is, so we take the difference of those two things and then take half of that in order to find a. That gives us a value of 3.5 for a. Now where is our vertex? Well, it's halfway through. It's at the midpoint of this line segment connecting the focus and the nearest point on the directrix. We could find that by going up by a from 5.5. So we're going to get the same x value, 10, because we're going to travel up. We're not changing our x value. But our y value is going to be 5.5 plus 3.5, which is 9. So this gives us a vertex right here at 10, 9. So we want to just now plug all of that in. We take 3.5 and put it here against the 4. 4 times 3.5 is indeed 14. And our 10 goes here with our x, and our k goes here with our y. We're opening up or down. So this is an x squared equals something y kind of setup, and we are also opening up because our focus is above our directrix, and so that makes this a positive 4 that we used here. For number 12, they want us to write the equation of a parabola whose directrix is at this value, and the focus is at this value here. So x equals negative 7.75 is a vertical line. We could mark that. The focus is going to be at negative 12.25 and minus 2. So just plotting that really quickly, that puts a focus right here. Now, the distance between this and our vertical directrix is going to be a horizontal line of symmetry through the parabola, and we're going to go a distance of 2a in order to get from the focus to the directrix. 1a, or right in the middle of those two, is going to be our vertex. So we take this distance from negative 7.75 to negative 12.5, and that's going to give us a distance of 4.5. Then we take half of that to get our value of a. To find our vertex, we could go up by a from negative 12.5 to bring us to 10. The y value is going to stay the same because this parabola is opening to the left. We can see that because the directrix is over here, a vertical line, so our parabola opens either right or left, and the focus is to the left of that, so the parabola opens to encompass the focus. Now we've got a vertex at hk, and we have a value for a, so we can just plug everything into standard form and simplify to get y plus 2 squared is equal to negative 9 times x plus 10. So question 13 is asking for something a bit different than what's come before. It's actually given us the equation for a parabola, but it's sort of in a general form and not the standard form. The trick to converting between any general form two-variable polynomial of degree 2 and a conic section is going to be to try to complete the square. So in other words, what we want to do is separate our x's and our y terms. Here I've left x squared plus 6x right where it is, and I've moved 32y and minus 55 over to the other side as positive 32y plus 55. In order to complete the square on x squared plus 6x, I need to add 1/2 of 6 squared. So that's 3 squared to both sides. That allows me to factor on the left-hand side as x plus 3 squared. And on the right-hand side, I get 32y plus 64. Notice that we can factor a 32 out of that, which gives me 32 times y plus 2. And 32 is in fact nicely divisible by 4, so we could write this as 4 times a whole number. That's nice, but even if this wasn't divisible by 4, we would still divide a 4 out. The reason is we want to write this with the 4 as per standard form to see what this value of a should be here. So even if this wasn't a nice number, I would still divide by 4 in this step. This lets us read off what the vertex and a are. We have a vertex at minus 3, minus 2, and we have a value of 8. So let's put all that together. We also notice the orientation from this standard form. It's an x squared, so we know it's opening up or down, and this term is positive here, so we know it's opening up. Over on this side, right, we begin at negative 3, negative 2, and we want to go up by 8 to get to the focus, down by 8 to get to the directrix. So we'd have a focus at minus 3, 6. We'd have a directrix at y equals minus 10. So our strategy here is going to be to convert something into standard form where we can read off what the value of the vertex is, distinguish what kind of orientation the parabola has, and then use that information to take a step by a away from the vertex to find the focus and the directrix. For 14, they want us to find the focus, directrix, axis of symmetry for the parabola, and they want us to graph it, okay? So the first thing we would do is take a look at the form. We notice that it's in standard form. We have an x minus h term squared here. This tells us that h is negative 1. We have a y minus k term here without a square. That tells us k is equal to 2. And we have a positive coefficient next to the y term. This tells us that we are opening up because the x is squared and this term is positive. We can also divide by 4 here to tell us that a is equal to 2. Let's begin with the vertex, which is easiest to see. This is at minus 1, 2. I like to begin with a sketch, so I would start by noting the orientation, putting a vertex at negative 1, 2, and then orienting the parabola up. If we go from here up by a units, we get to the focus, which is therefore going to be at negative 1, 4. And if we go down by 2, we're going to get to the horizontal line, which represents our directrix. It's horizontal because this has got to be an upward facing parabola. And going down by 2, that'll give us the x-axis, or y equals 0. The axis of symmetry of the parabola is the line that cuts it in half. That goes through the focus, the vertex, and the nearest point on the directrix. It's a perpendicular line to the directrix. So in this case, it's the vertical line passing through the vertex, which is going to be at x equals -1. Here is a graph of that. So I've put my vertex here at -1, 2, and we know it opens up. We know the directrix is right here, and we know the focus is right here. Now, if you want to know 2 additional points, it's totally fine to try to plug in some points and, graph the parabola that way. But there is always going to be an easy series of points that we can plot. And that is using this sort of additional figure that we haven't talked about yet called the lattice rectum. The lattice rectum is a chord which stretches across the parabola. It's parallel to the directrix, and it's of length 4a in total. If I go 2a from the focus, I get to a point on the parabola. And if I go another 2a in the other direction, I get to a point on the parabola. This is something that's useful because it gives us 2 easy points to plot. If I just plug in some points, I can evaluate to find out what y should be, but I might get some weird fraction. On the other hand, if a is a whole number and the vertex is at a whole number, these 2 points across the lattice rectum will be a whole number as well. This gives us an easy point, for example, 3, 4 here, that we could plot using the vertex. I know in your homework you select a vertex for a parabola and then you select one additional point and it'll draw it through. You can use this lattice rectum trick to find that one additional point pretty easily, as long as you remember what a is. For this problem, a was equal to 2, and so if we go 4 units to the right from our focus, we're going to be on the parabola. Question 15 also asks us to find the vertex, focus, and directrix of this parabola. We first note that its orientation is left-right because y is squared and x is not. We then note that this leading term next to the x is negative, and so this is a left-oriented parabola. We see it has vertex at -3, -2, and the value of a is going to be 4. So if we go down to -3, -2, and we go 4 units to the left, we're going to be at our focus. And if we go 4 units to the right, we're going to be at the vertical line, which represents our directrix. That gives us these values here. Moving on. Question 16 asks something very similar. We note this is orientation up or down because x is squared and y is not. We notice that the leading term here is negative, and so this is orientation down. The vertex is at 2, -3, and if we divide this by 4, we get that the a value is 6. So the fact that it opens down means if I put my vertex here, I'm going to go 6 units down to plot my focus, and the parabola is going to wrap around that. Then if I go 6 units up, I'll get to a horizontal line, which represents my directrix. That'll correspond to these values here. Moving on. Here we have some where we're just asked to graph the parabola. I've actually graphed a little bit more, but if you strip away some of the bobbles here, you could just graph the parabola. Let's talk about it. So this one has a value of 1. It's got a vertex at 2, -3, and it is rightward opening. The y value is squared, this term is positive, and so this opens to the right. That's going to let us pick a vertex, pick our focus, wrap the parabola around that, and then going the same distance to the left, we have our directrix. If we wanted 2 more points to plot on this parabola, we could go from the focus up by 2a and down by 2a to get to these other 2 points across the chord of the lattice rectum. For the next one, we're asked to graph again. We notice that x is squared, y is not, so this opens up or down. We notice this is negative, and so it opens down. This divided by 4 will give me a 4, and so that is our value for a. We are at 1, 3 for our vertex. So if we put 1, 3 here, and then go 4 units down to mark our vertex, we are going to see this is a downward-facing parabola. We go 4 units up, and we plot our horizontal line, which is our directrix. And then if we want 2 more points on the parabola, we could go over by 2a to plot another point. Actually, if I go over by 2a here, I'm slightly off the edge of the map, but we could at least get this second point for plotting on the computer homework by using this 2a trick with the lattice rectum. You could also plug in some points here that would tell you about where you should go, but it's hard to see what's a whole number and what's not. This lattice rectum trick gives you a nice clean point that you can plot. Question number 19 asks us about a satellite dish shaped like a paraboloid of revolution. Paraboloids, ellipsoids, hyperboloids, all of these OID shapes, what they are is three-dimensional shapes that you get by rotating a, in this case, parabola. But if you take a figure and rotate it around its axis of symmetry, you can trace out these kinds of shapes, and they preserve some of the properties of the conics that are used in rotation to create those shapes. This is one of the reasons that they are used as a receiver. I'll discuss that in just a second briefly, although I won't give a full proof of it. The question here says that if this dish is 48 feet across, where should I put the receiver, which will be at the focus? We notice that it's 48 feet across and 6 feet deep. So what we want, first of all, is to note that every cross section across the diameter of a surface of revolution is going to give me the same shape. And we can use that shape to work from. We don't have to think about this in 3 dimensions. We can cut it across any section and look at that parabola, right? It's easier to do that than to try to think about all 3 dimensions at once. We take a slice of it and work with the shapes that we know. Now, I'm going to draw this parabola down here a little bit more to scale. They say that it's 48 across. So if we kind of conveniently put the vertex at the origin of some coordinate system, then we know that this is generally the shape of our parabola. We know it goes through 0, 0. We know it goes through 24, 6, and we know it goes through minus 24, 6. If you remember the chapters on matrices and linear equations, that's actually 3 points, and so determines a single parabola. We could figure out what this parabola is using those linear equations and matrix methods, but let's use some of the information from this chapter. For example, since it's an upward-facing parabola, we know it has this form, and we also know that it goes through 24 at 6. This is going to be enough to let me solve for A, which is going to be 24 itself. That means we're going to want to place the focus of this parabola at 0, 24. That's going to look something like this. Now, just to briefly discuss why a parabola is being used in this way, it's a curious property of parabolas that reflections take parallel beams back into the focus. We're not going to prove that. It's just a really interesting fact, and it's the reason that we use paraboloids when we are making parabolic mics. A parabolic mic can take incoming sound and reflect all of those waves back towards a common receiver, which helps strengthen weak signals. All right, that's going to do it for this video. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next one.